Okay, guys, we'll make a start then. Like I say, it should be a fairly quick one today. Won't go more than 25-30 minutes, I promise, hopefully. We're going to be looking at Group 1 and the transition metals today. There's some similarities and differences you need to be aware of, and I'll just go through those so it'll help you fill in the assignment that I've set for you this week. So before we start, we're just going to do a quick recap on metallic bonding. So I'm just going to slide that over there so you can see. So metallic bonding, this is the bonding in any metal. So it could be one of the group 1 metals, so sodium, lithium, potassium, could be one of the group 2 metals, calcium, strontium, and so on and so forth. It could even be a transition metal like iron. So all metals have this bonding. And the key thing, like I said last week, metals want to lose electrons. They want to lose electrons. So how, if you've got all these metal atoms wanting to lose electrons, what does their structure actually look like? Well, first thing is they're arranged in layers, but they're not exactly atoms because let's take sodium, for example. So these are sodium atoms. And sodium is in group 1, okay? So sodium is in group 1, which means that it has 1 electron in its outer shell. Therefore, it needs to lose that electron. So if it loses that electron, it becomes a positive ion, like so. But where have all those electrons gone? Well, they've been delocalized. So those electrons are just effectively swimming around in between the individual ions. So you've got, this is the basic structure of any metal. You've got these layers of positive ions, and surrounding them, you've got this, I'm going to use this phrase, it's very popular in GCSE Chemistry, a sea of delocalized electrons. Okay, so how does that hold the structure together? Well, you've got positive metal ions and you've got negatively charged electrons, and there is an attraction there because opposite charges attract. So there's a metallic bond there. Any attraction between, wherever there's a positive and a negative in close vicinity, that is what metallic bond is. So it is a strong electrostatic attraction between positive metal ions and delocalized electrons. So what does that actually mean? Let's go back to the delocalized part. Delocalized just means not localized. So delocalized just means it doesn't belong to any individual sodium ion. It's just swimming and floating and running in between all of these different ions, and you end up with all kinds of metallic bonds, or loads and loads and loads and loads of metallic bonds. And because of that, all metals tend to have similar properties. They all conduct electricity. Why do they conduct electricity? Because these delocalized electrons move through the structure. So that means that if this whiteboard, for example, was a piece of metal, I could hook up a crocodile clip here to a power pack, hook up a crocodile clip there to a power pack, and the electrons are able to flow through the structure, through the whiteboard. Therefore, it's able to conduct electricity. And where students tend to mess up on that is that it also conducts heat as well. So when you heat a piece of metal, the particles start to vibrate, the electrons will start to gain kinetic energy, they'll move faster, the electrons will move through the structure, and that kinetic energy is transferred into thermal energy, and it will carry heat all the way through. Okay, so that's the key thing about this thing. Another thing as well, because they're arranged in layers, these layers can slide over each other. And because they slide over each other, without breaking the bonding, you can actually bend metals. Okay, we say they are malleable. They are malleable and they are ductile, which means they can be drawn into wires. So if you ever had a piece of metal, right, you should be able to bend it quite nicely. If it's a pure metal. If it's an alloy like steel, alloys are a lot harder. than pure metal. So steel is actually very, very tough to bend. So there we go, and that's basically what you need to know for metallic bonding. So whether it's group 1 or the transition metals, the bonding is always like that. Yeah. The only difference will be the size of the atoms, because not all of the atoms are the same size. The charge as well. So if it was in group 2, for example, it would be a 2+ ion. If it was in group 3, it'd be a 3+ ion. And the transition metals, you can actually get various different charges, and I'll come on to that later. So that's the structure of any metal. So we're going to be looking at group 1, the alkali metals, and the transition metals for a comparison. Okay, so let's start with that. Any questions before we move on? Good. Hi, Macy. Superb. Right, so we'll make a start. Let's just move over to here. So what do we know about the alkali metals? So group 1, okay? Well, the first thing is they've got 1 electron in their outer shell and they want to lose it. So that tells us that they form +1 ions. So they lose electrons to form +1 ions, okay? What else do we know about them? Well, they are actually quite soft. They're actually quite soft. From the videos you would have seen on the alkali metals being cut up and chucked into water, you can actually cut them with a knife quite easily, actually, and they get softer as you go down the group. So if you had a piece of potassium, for example, it cuts like just cheese effectively. At the top of the group, it still cuts it, but it takes something a bit sharper to get through it. So they're soft. Brilliant. What else? They've got low density. So low density, what does that actually mean? Okay, well, low density means that most of them, I'll say most, actually half of them float on water. And that's quite unusual because you think about metal, you can try this at home actually, all the metals you've got at home will probably be made of transition metals or derivatives of them or alloys of them. And if you put them into a bath or a washing up bowl, metals tend to sink. But quite a few of these, all right, tend to float. I'm going to put float on water. Okay. Right. So what else do we need to know about them? Well, hopefully we know from last week that these things are very reactive. Yeah. You would not make your water pipes at home out of a transition metal because out of an alkali metal, because they react with the water straight away and you'd end up in all kinds of bother. All right, so they are very, very reactive. And remember the trend, they get more reactive going down the group. So group 1 metals get more reactive going that way. It gets easier for the atoms to lose their electron and have a full outer shell. Okay, what else? Yeah, let's look at the compounds they form. So these tend to form, all right, white compounds. Okay, and I'll put e.g. salt. So if you think of salt, Ashton just saying that he would make his pipes out of cesium. Well, your pipes wouldn't be around for very long, Ashton. It would go boom straight away. White compounds, so salt. So salt is obviously white, sprinkle on your chips, put it on your food, etc., etc., etc. But what is the metal ion within salt? I'll let someone put that onto the chat right now. What is the metal within salt? Yeah. It is incorrect. It is sodium. So sodium is in group 1 and sodium chloride, which is table salt, is a white compound. So group 1 metals tend to form white, in fact they always do form white compounds. And these are things which are common to any sort of group 1 metal. What else will the group 1 metals do? Well, they'll do whatever any metal does, okay? So just going back to this list over here. So I'm just going to erase a little bit to create some space. So what do all metals do? All metals do the following. Okay, so I'll just put properties here. They conduct heat and electricity. That's one thing they do. They are malleable, so they can be bent. Okay. They tend to have high melting points. All right, so I'll just put that down as another one. And they're also ductile. And ductile just means it can be drawn into wires, so you can make wires out of them. Okay? So the group 1 metals will do all these things, but they'll also do these. Form +1 ions, they're soft, low density, very reactive, white compounds. Their melting points are actually lower than usual. So I'll put relatively low melting points compared to most other metals. It links into how soft they are and how dense they are. You can actually melt, I don't recommend you do this, cesium in the palm of your hands because the melting point is about 28 degrees Celsius and your body temperature is about 37 degrees Celsius. So that's what these things do. And again, if you learn these this list of facts here, you sort of can automatically predict what the transition metals are going to look like in terms of their properties. So first thing is the transition metals have different ions. So it could be, e.g., +1, +2, +3, +4, etc. So depending on the transition metal will depend on how many electrons it loses to become stable. And that's why they're in between. So if you look at the periodic table, the transition metals are in between groups 2. So I'll draw a quick crude diagram here. Okay. So you've got group 1, 2, 3, 4, 5, 6, 7, and then group 0, the noble gases. The transition metals are just here. Yeah, they're the transition metals. And they can lose different amounts of electrons depending on the metal. The reason why is actually, it's above GCSE, but I'm going to tell you anyway, is because these things, the transition metals, all right, can hold more electrons in, well, if you just take the first row, for example, those transition metals there can actually hold more electrons in their third shell. So you know that you've heard of 2,8,8,2, yeah? That is calcium, which is just there on the periodic table, okay? Well, technically, if you were to take something like, I don't know, let's take copper. Copper would be 2, 8, 12, 2. So you can see that the transition metals can actually, and when you get to A-level chemistry, I'll explain this in a bit more detail, the transition metals can actually hold more electrons in their third shell. And then fourth shell, fifth shell, and sixth shell as you go down. You don't have to worry about why, all right? In fact, you don't even have to know that because it's not in the GCSE specification anymore. But I'm just letting you know that the reason why the transition metals can do things a bit different is because they can hold more electrons in their third shell. And they can also lose electrons from that shell as well, which explains a couple of other things they do. So I'm just going to erase that. Okay, so they form different ions. Good. What else do we get? Well, we said alkali metals are soft, so what do you reckon the transition metals will be? Well, you'd be guessing correct. They tend to be harder and stronger. Okay, so harder and stronger. So you would make your copper pipes out of, you'd make your water pipes out of copper because copper is a transition metal. It is harder and stronger than a group 1 metal. But don't forget, just because it's harder and stronger, it can still be bent because it is a metal. Okay, so, right. Next one, low density for the group 1 metals. So the transition metals have a high density. Why do they, well, just way the atoms are arranged differently. Some of you are going to ask questions this, why are they low density, why are they high density? Well, you can see here, all metals have this type of structure. Let me just go back to the metallic bonding bit. Okay, but I've arranged them in nice layers of 3, 3, 3, 3, 3. It might be they've got irregular layers, and like I say, the group 1 metals have got a certain crystal structure in terms of the atoms are arranged. The transition metals have different. Mercury has an even more different one because mercury is a liquid at room temperature, but it is still a transition metal. Okay, but again, we'll discuss more of that when we come back from school closure. So they've got high density. They are pretty unreactive. Unreactive fairly. So they do react, but they don't react as well as the group 1 metals, which is useful to us because metals we tend to use for things like buildings and reinforcements. You know, we need strength, and we don't want them reacting with either water in the air or oxygen in the air around it. So they're pretty unreactive, and they do tend to form coloured compounds. Coloured compounds. So, for example, Statue of Liberty. The Statue of Liberty is covered in copper carbonate, which contains copper and is that lovely sort of green colour. So again, they form coloured compounds, which is something else that the transition metals don't. That the alkali metals don't. That, by the way, we do a whole topic on in year 13 chemistry, why the transition metal compounds are coloured and these aren't. The reason why they're coloured is going back to the thing I was talking about earlier in terms of the electrons, because their third shell can hold a lot more electrons than the rest of the metals on the periodic table. Okay, and that's pretty much it in terms of a comparison. I'm just going to put your worksheet on the screen over here so I can see. Okay, have we covered everything? Yeah. So you should have enough information now to have a go at, just zoom in a bit for that, this particular task. Yeah. So just looking at the task, I'm going to read them out. Do you know which ones have got relatively low melting points? Hopefully that's on there somewhere. Which ones have got high melting points? That will hopefully be on here somewhere, just now. Yeah, you've got the reactive, unreactive, catalyst. Good question. Which of these two do you think would act as a catalyst? So a catalyst is something that speeds up a reaction. Something that speeds up a reaction. Would you want a group 1 metal or a transition metal? Have a think to yourself now. If you wanted a metal to speed up a reaction, would you use this or would you use that? All right. Just think about it and then come up with a reason why you do that. Nice thought, right? So this is a very, very, beautiful. Loads of people saying group 1, which is fantastic, because that's wrong, all right? You want a catalyst to speed up a reaction, but you don't want it reacting with your reactants. So for example, if I had A plus B makes C, if I wanted to speed that reaction up, I'd add a catalyst. But do I want my catalyst reacting with any of these things? No. All right. I want it to speed the reaction up, but I don't want it to sort of take part in the overall equation. So what you do is you use a transition metal. Transition metals are super good catalysts. Because if a catalyst speeds up a reaction without getting used up, then basically it goes in at the start, speeds up the reaction, and it's still there at the end. And the reason why the transition metals can do this, and I'm going to do a bit of year 13 chemistry with you now, is because if we take iron 3+, for example, iron 3+ can turn into iron 2+. Yeah, so iron 3+ can turn into iron 2+ by gaining electrons. That can then turn back into that. So because they've got these different ions, they can actually take electrons and then give electrons back to other things, which means they're really good as catalysts. So the transition metals, and that's true for all transition metals, are really good catalysts. Imagine if you started chucking a piece of potassium into your reaction. It's going to react straight away, not just with what's in the beaker. It'll react with the moisture in the air, it'll react with the oxygen in the air. So again, you wouldn't use these things as catalysts. Okay? And like I say, that's pretty much a brief summary, if you like, of the transition metals and the group 1 metals. I'll just go through your worksheet now, make sure that I've covered everything. High density, low density, yep. These obviously react with water to form alkali solutions. How do we know that? Well, what do we call group 1 metals? They are the alkali metals. Yep. And strong, hard, soft, cut with a knife, high density, low density, forms +1 ions, forms different ions, and reacts with, forms ionic compounds when they react with non-metals. So again, because they're both metals, they will give electrons to non-metals. All right. Okay, right. That's pretty